Alright, so here we're going to focus in on some logarithmic equations. We're going to look at the special property which says if I'm taking the log on both sides of my equation and my bases are the same, then whatever I was taking the log of has to also be the same. However, if you can't apply this rule, then you have to apply one of the other rules together. For example, you may have to combine your logs together using some of the log properties. And if that still doesn't work, then you have to apply some of the other log rules that we have in place. So for example, we have the log base 4 of x minus 3 plus the log base 4 of 2 is equal to 3. So with this, the first thing we have to notice is that I very clearly have the product rule. So the first thing I need to do is apply that product rule. So this says I'm going to combine my logs into a single log, where this becomes 2 times x minus 3, and the whole thing equals 3. Then I'm going to use an exponential rule. So I want to apply the rule that says if I make my exponential base and my log base the same, then whatever I was evaluating by spits out as the result. So here my base is 4. So this is my base. So I need to raise both sides of the equation into an exponential form where it has a base of 4. So I have 4 to the log base 4 of 2 times x minus 3 is equal to 4 to the third. Now this part right here is going to undo itself, purely because the base of my exponential and the base of my log are the same, and it's going to leave behind just what I was evaluating by. So this becomes 2 times x minus 3 is equal to 64, which is 4 cubed. And then I simply have to solve for x. So I'm going to divide everything by 2, add 3 to both sides, and you end up with x being 35. Okay. So for this one, the only thing that we had to remember was to condense using the product rule, and then to apply this really handy exponential rule, which removes the log out of the problem. So let's look at another one. Here I have e to the 2 natural log of x, and then I have 4 log of 10. So the first thing that we need to note is that this right here is going to follow the power rule, which says it is going to put it right back where it belongs. And then the second thing we need to notice is that this right here is actually a common log, which, if you remember, common logs are log base 10. So if you notice, this is log base 10 of 10, which means log base 10 of 10 is going to become 1. So here we have to look at what's left. Well, this becomes e to the natural log of x squared is equal to 4. Because of this little rule right here, that log base 10 goes away and leaves just the 4 behind. Now, the other thing that we have is that my natural log and my e are going to undo each other. Therefore, that is going to leave behind that x squared is equal to 4. So we can take the square root and we get that x is equal to 2. Now remember, you cannot take the log or the natural log of a negative number. So we're just looking at the positive in this case. Let's look at another one. Here I have 2 natural log of x plus 3, and then I have the natural log of 12x. So the first thing I have to look at is I have to look at what can I condense. Well, right here off the bat, I have a power rule which says this needs to come and resume its power. So this becomes the natural log of x plus 3 squared equals the natural log of 12x. Now in order to undo the natural log, I just very simply would raise each side to the e. So if I raise this up to my e, then my e in natural log, this right here, will go away. Same with this. And it's going to leave behind x plus 3 squared equals 12x. So in order to solve for this part here, I have to FOIL it out. Now FOIL does not mean square the first, square the second, call it a day. What it means is you have to do first, outer, inner, last. What this actually says is that I have x plus 3 times x plus 3. So I have to multiply that together. First is going to be x and x, which is x squared. Then I have my outer, which is 3 times x, so this is plus a 3x. My inner is plus a 3x, and my last is plus 9. So this whole thing equals my 12x. I need to keep combining my terms, so I have that x squared plus 6x plus 9 equals 12x. So here, what we actually have is that x squared minus 6x plus 9 equals 0. So how did we get that? We took this 12x here and we moved it this direction by subtracting, thus combining my terms. So now I need to solve. So I can solve this into its factors. And the reason I can break it into factors is because my a term here has a power or a coefficient of 1. So this becomes x and x. My back term here is positive, so remember that tells you your sign choices that you could possibly have. And remember, your choices are as follows. So your choices would be positive times positive gives me a positive. Negative times negative gives me a positive. Or positive times negative gives me a negative. So this sign right here tells you which of these choices to choose. So notice I can only choose between these two because they're the only ones that are positive. So this one here does not work. And then this middle sign is going to tell us which choice we have to select. So we have to use our negative choice because I have to add to a negative. So that right there tells you that your signs of your factors both have to be negative. And so here I now need factors of 9 that will give me 6. And in this case, those happen to be 3 times 3. So notice what I actually have here is x minus 3 squared equals 0. Take the square root of both sides. X minus 3 equals 0. So x equals 3. So here what you should take out of this problem is that even though you're doing a natural log problem, having to solve quadratics still comes into play. Okay. Now let's look at one that's got a little bit more to it. So here what I have to notice right off the bat is that I have the quotient rule. So the quotient rule says first is the top, second is the bottom. So here this one's going to go on top, this one's going to go on bottom. And this means I can rewrite it as the log base 3 of x plus 1 over x minus 4, and the whole thing equals 2. Again, I want to apply that fancy rule, so I want to apply the rule that says a raised to the log base a of x will give me x as a simplified result. Well, in this case, my base here is 3, so this is your base. So I have to log or raise both sides into an exponential. So this becomes 3 raised to the log base 3 of x plus 1 over x minus 4 is equal to 3 raised to the 2. So my log right here, this is going to go away. So this is going to undo itself according to the rule, and just leave behind x plus 1 over x minus 4 is equal to 9, because 3 squared is 9. And now I need to solve for x. So to do that says I need to multiply both sides by x minus 4. So this leaves me with x plus 1 is equal to 9 times x minus 4. Distribute your 9 into both parts. So you get x plus 1 is equal to a 9x minus 36. And then I need to do a little magic, and one thing that I would do is, because I have a bigger 9 or bigger x value on this side, I would take this x and move it this direction through subtraction, which means I need to take this 36 and I need to move it in the opposite direction through addition, and I move it through addition because it's negative. So I have 1 plus 36 gives me 37, and I have 9 minus 1 gives me an 8x. Divide everything by 8 and you get 37 over 8 is equal to x. Okay. Now, along with logs and exponentials, we have some applications. And so again, we need to remember the formulas that you have to use with those applications. So this first one up here is population growth, where P0 is your initial population. The next one down is your half-life. Half-life is a decaying function. So it's talking about how long it takes a substance to reduce down half its size. Then we have doubling time. Doubling time is where we're looking at how long it takes a substance, for example, usually bacteria, in order to double in size. And so we're looking at how quickly is this growing. Doubling time becomes important when dealing with viruses or any kind of bacterial agent or any growth agent, where you're wanting to know how quickly something is expanding or growing or multiplying in its numbers. Then of course we have that good old-fashioned compound interest, as well as compounding continuously. Last but not least, we have carbon-14 decay. So remember, that is your radioactive carbon dating. We use that a lot of times when you are doing dating of objects and you want to know how old an object is. Carbon dating comes into play. So we are going to use a variety of these different equations to solve some different problems. So here we have, assuming the half-life of 5,728 years, how long would it take for 3 grams of carbon-14 to decay down to 1 gram? So the first thing that we need to note is which equation to use. And we're told right here, carbon-14. So we are going to use the equation A of t is equal to my A naught e to the negative 0.000121 t. Now, we've also been told a couple other things. First, we've been told that my initial is 3 grams. So we know that A naught is going to be 3 grams. We also know that the ending result, or my A of t value, is 1 gram. What we want to know is how long it's going to take for that decay to take place. So here, what we care about is that we have 1 is equal to 3 e to the negative 0.000121 t. So we need to solve for t. So the first thing I would do is divide everything by 3. So this becomes 1/3 is equal to e to my really long decimal. The next thing I would do is take the natural log of both sides. That's going to cancel out this e value. So I'm going to have the natural log of 1/3 is going to equal just what's left over in the exponent, negative 0.000121 t. And then the last thing you need to do is you need to divide everything by that crazy decimal. So we have that t is equal to the natural log of 1/3 divided by negative 0.000121. So we need to go ahead and work this on your calculator. So here's our trusty calculator. Now remember, this is mine. It's that TI-36X Pro. So your calculator may be slightly different from the one that I'm using. And so here, I would start with the top. So I'm going to turn or hit my natural log button. I'm going to then type my 1 divided by 3, close it, and I'm going to go ahead and hit enter. And then I need to divide this number by the bottom. So I'm going to hit my division. I'm going to open a parentheses and do negative 0.000121. Close your parentheses and hit enter. So this tells us it's going to take 9,079 years, 0.44. Okay, so here my t is going to be 9079.44 years. Okay. Alright, let's look at a different one. Suppose a population of bacteria in a petri dish has a doubling time. So this right here, doubling time, is your important piece, of 1.5 hours. It says, how long will it take for an initial population of 10,000 bacteria to reach 100,000? So the first thing that we need to know is we need to write down the equation we're going to use. So we're going to use P of t is equal to P naught, and then it's A to the little t over big T. So there's some information that we need to know here. First, P naught is your initial amount. P of t is your ending amount. Now we have a couple other terms. Little t here is going to be your time. It might be in hours, for example, could be more. And usually this part might be what you're solving for. Big T is what's called your doubling time. So a lot of times this is also in hours. And then we have this A value here. Well, because we are doubling, then A has to equal 2 because we are doubling in size. Okay? So we are doubling our size, so A is 2. So that's how this formula is going to work. So based on our problem, what do we know? We know my P of T, or my ending amount, was 100,000. We know the starting amount is 10,000. We know my A is 2 because we're doubling. We know my big T is going to be 1.5 hours because we're told that's the actual doubling time. And little t is the unknown. That is what we're solving for. How long does this happen? So we need to set up our formula. 100,000 is equal to 10,000 times 2 raised to the little t over 1.5. So we need to be able to solve for little t. First things first, divide both sides by that 10,000 to reduce my numbers. So we have that 10 is equal to 2 to the t over 1.5. In order to pull my exponent out means I have to be able to pull on my log power rule. So I have to take the log of both sides. So this becomes the log of 10 is equal to the log of 2 to the t over 1.5. This right here is now my power rule, which says it can come down in front. And this right here is my common log, which says that I have the log base 10 of 10, which equals 1 as a result. Therefore, 1 is equal to t over 1.5 log of 2. I need to multiply everything by 1.5, so this becomes 1.5 equals t log of 2. Divide everything by log of 2, and I get that 1.5 divided by the log of 2 equals my t. Again, pull out and plug into your calculator, and you should come out with roughly 4.98 hours. So what this means is that it's going to take almost 5 hours for your population of bacteria to increase its size from 10,000 to 100,000. Okay, and that is doubling time. Now the last one I wanted to look at is an investment. So here I have that Wayne has $12,500 in a high interest savings account at 3.66 annual interest compounded monthly. So this compounded monthly tells you right now we are using A equals P times 1 plus R over N to the NT, i.e. we're using the compounding equation, not the continuous one. So assuming he makes no deposits or withdrawals, the question wants to know how long it will take for the investment to grow up to $15,000. So we have 15,000 is equal to my 12,500 times 1 plus my rate 0.0366 divided by monthly, so divided by 12, raised to the 12t. And t is what we need to solve for. So first I need to divide everything by that 12.5. So I get 1.2 is equal to my 1 plus 0.0366 divided by 12 to the 12t. In order to pull this down, you need to take the log of both sides. So this becomes the log of 1.2 is equal to the log of my stuff, 1 plus 0.0366 all over 12 raised to the 12t. Now we can apply our power rule. So my power rule sits right here. This is the power. And the rule says the power is going to come down in front. So this becomes the log of 1.2 is equal to 12t log of my stuff, 1 plus the 0.0366 over 12. And notice I have not done the math inside my parentheses here. I am saving that for the point when I am actually ready to start solving. Because what you don't want to do is you don't want to round early on in your problem and thus cause mistakes or issues down the road. So I want to save all of my calculator work to the very end. So I would leave these parentheses alone till you get down to the bottom. And so here I simply have to divide everything by 12 log of my stuff. So I get that t is equal to the log of 1.2 over 12 log of 1 plus 0.0366 over 12. So that would be considered your exact answer, but since we want to know how long it's going to take, we need to actually solve this down, which means we need to pull on that calculator. So here we go. So I'm going to work from the bottom and I'm going to work from the inside out. So we have 0.0366 divided by 12 and hit enter. Now we're going to plus 1 and hit enter. Now I'm going to do the log of that answer and hit enter. I'm going to multiply that by 12 and hit enter. Now I'm going to save this as that answer result, and I'm going to do parenthesis log of 1.2 and divide that by my answer, and I get 4.989 years. Okay. In other words, really, really close to 5 years. So that's kind of everything in a nutshell about logarithmic equations and some of the applications and how to solve those equations. So if you have any questions, please let me know. Otherwise, see you next time.